Hello, everyone. Here we are in Chapter 10, Section 5, and we're going to talk about tangents. Okay, guys, thank you guys for my little music interlude. A long time ago, I used to be a DJ on the radio, and so I kind of miss music. And so maybe we should start doing music in math. Maybe not. All right, we're going to talk about tangent. And I know you're like, I know tangent. I know tangent is one of the friends of sine and cosine. And I'm sorry, mathematics kind of did a doozy on us when they used the same word for different concepts. So this tangent is a little bit different. If I have a circle and I have like a line that passes right through one point on the circle, I know that's hard to see, but let's pretend it just goes through one point. That is called a tangent. All right, so a tangent of a circle could be a line or a segment, or you could have a triangle that's tangent to a circle. To say, oh, that triangle, it's tangent, right? There's a little tangent situation going. You could have circles that are tangent to one another, right? You could have, I don't know, whatever. Lots of things could be tangent to a circle. It just means that it intersects the circle in exactly one point. So that's what tangent means. Now we need to talk about point of tangency. I think you guys already figured it out. It's the point where the thing is tangent to the circle. So this segment is tangent at that purple point. This triangle is tangent at that purple point. And this circle is tangent to the circle, where it's the point of tangency, at this particular point. Common tangent. A common tangent would be this segment that I'm going to draw as best I can. Nope, that's not it. I missed it. I'll try it again. This tangent that I'm going to draw right here and right here. Can you tell me what common tangent means now? It means a tangent that is commonly tangent to more than one thing or more than one circle. So this is a common tangent. These two circles have a common tangent. That common tangent is line L. I'll make it a line. Make sense? So that's our vocabulary. Let's get started with some examples. So here we're supposed to copy the figure and draw a common tangent. If no common tangent exists, then we write no common tangent. Simple? Yes, of course. Let's go ahead and see what we can do. I'm going to use my black pen, and this guy would be kind of an example of the last one we saw. Let's pretend I did a better job of drawing that. And that has one common tangent right there, right? These two circles have one common tangent, and they have another one right about here. Right about here. So this figure has two common tangents. You guys see that? I know it's not as neat as you want it to be. And this one has the same kind of two outer common tangents that we see there. Let me try it again. I'm going to get this right. One of these days I'm going to really know how to draw straight lines, and everyone will be impressed. They will all cheer for me. All right. And then this one is another common tangent. So far we've got two common tangents, but there are others. These interior tangents that I'm going to draw are also common tangents as well. You guys see what I'm doing? So this line, this red line, is tangent to both of those circles. And you can guess that there's yet another one that I will try to draw that intersects each circle in exactly one point. I'm stretching it there, but you guys know what I'm talking about. All right. So this figure has two common tangents. This figure has four. What is a geometry lesson without theorems? So here's Theorem 1010. In a plane, a line is tangent to a circle if and only if it is perpendicular to the radius drawn to the point of tangency. All right, so what we're hearing here is this line L is tangent to the circle only if the little segment that I'm drawing here is perpendicular to that line. Let's go back the other way because it's an if and only if, which means it can go in either direction. If I have some random line that's a part of this, that's here a part of the circle, and if I draw a radius to that line and that they create a 90-degree angle, then I know that line is tangent. So first, if I got a tangent line it's going to be perpendicular to the radius at that point. If I have some line that's perpendicular to the radius at that point, it's tangent. Think about it. It's wonderful. Okay, well, kind of confusing, but let's see if we can apply it anyway. So in this example, we're supposed to identify whether we got a tangent or not. JL is a radius, confirmed, of this circle J. Determine whether KL is tangent to circle J, and we're going to justify our answer. The only justification we have is if we can prove that this angle formed by these two segments here, if they form a 90-degree angle, by that last theorem, by theorem 1010, we know that KL is tangent, right? Because of the 90-degree angle situation. So how can we prove that this is a 90-degree angle? That's the question. Any ideas? I'm hoping somebody's thinking, well, clearly we learned about the Pythagorean theorem, dear teacher. And if we can apply the Pythagorean theorem to the sides, then we know indeed it's a right triangle because, you know, that's how it goes. So let's hope for the best. Now, right now this looks a little bit weird because this is 15, this is 8, and this whole thing is 9. No, just those little bits 9. So that means from here to here, let's call this D because that's a great letter. Let's say D right here. Then we know that from D to J is 8 and from K to J is 17. So as we try to apply the Pythagorean theorem to see if this is a right triangle, to see if this is a right angle, to see if this is a tangent, we need to make sure we're talking about the right numbers. So let's call A 8 squared. Let that be the altitude, and the base is 15. So 15 squared. And let the hypotenuse be 17. And so if this is true, I'll put a question mark over it. If this is an equivalent statement, then we're good to go. 8 squared is 64. 15 squared is 225. And 17 squared is 289. I'm pretty sure that's what it is. So if I add these guys up, are they equal? Drum roll, please. Okay, no drum roll is necessary. 5, 9, 2, 8. Woohoo! It is the truth. So yes, this is a right triangle. Yes, this is the right angle. And yes, therefore, KL is a tangent line to this circle, is a tangent segment to this circle. Feeling good. All right, so now that we've got that under our belt, let's look at example 3. JH is tangent. Okay, the fact that it's tangent gives me the fact that this must be 90 degrees. That's an automatic from our theorem 1010. Remember, it goes in both ways. Find the value of x. Okay, we can do it. We see that this is 90. This is a right triangle. I think we're going to pull out our a squared plus b squared equals c squared because we're dealing with the sides of a right triangle. That only makes sense. And we see that one side is x, so let's call that x squared, and this side is 12. And the c side is 8 plus x, so 8 plus x quantity squared. And so what we're going to do is we need to actually FOIL this. And foiling, or extended distributive property, whatever you want to call it, is how we're going to get through solving for x. Well, 12 times 12 is 144. We've got the x squared here. Let's see what happens here. If you remember from algebra, when we multiply two things like this, we're going to multiply 8 times 8, 8 times x, then x times 8, and then x times x. Once I do all of that stuff, I'm going to end up getting 64 plus 16x plus x squared. If this is baffling to you, if you don't remember it or if you need some help, let me know. I will happily give you a little refresher for your Algebra 1. These guys get canceled away. No need for those anymore, right? Because I can subtract the same thing on both sides. So I'm left with a much easier problem. 144 is equal to 64 plus 16x. Subtracting 64 on both sides, I'm left with 80 is equal to 16x. Dividing both sides by 16, I'm left with x equals 5. Boom. So x equals 5. We answered the question. Theorem 1011 tells us that if two segments from the same exterior point are tangent to the circle, then they are congruent. So we start at this exterior point, some point B out in the universe, and then B shoots rays to circle D, pew, pew, such that those rays are tangent. I know I sound crazy, but you know, gotta live a little. Then what we know by virtue of this point sending these two rays such that they are tangent to the circle D, we know that these two segments are congruent. That's what this theorem is telling us. If these two segments are tangent to D, then these two segments are congruent. All right? All right, let's see if we can apply that. I love these examples. They fit right into the theorem that we just learned. So we're going to use congruent tangents to find the measure. So given this circle, the fact that these two are tangent, we know that these two are equal, then we can solve by setting the two expressions equal to one another. So you guys see what we're doing? You know what this is. We're going to solve for x. 15 is equal to x minus 5. Add 5 to both sides. We see that x is equal to 20. Not too bad. We've solved for x. So we've talked about inscribed and circumscribed. Sometimes we can have polygons that are circumscribed about a circle, meaning they're on the outside as opposed to being on the inside. So when you have circumscribed polygons, they're tangent to each side of the polygon. These guys are not circumscribed because each side of the polygon isn't tangent to the circle. Are you guys with me? So circumscribed polygons, not circumscribed polygons. So with that, let's go ahead and take a look at what we're working with here. Here's a real world example where we have a graphic designer who is giving directions to to create a larger version of his triangular logo shown. If triangle ABC is circumscribed about, meaning around, that circle G, find the perimeter of triangle ABC. All right, so we got a little fun to do. Let's see how we can do it. We were given some parts. We're given this side. We know the perimeter is the sum of all sides. So what we're going to need is to find these sides, this side here, and this side here, and then we can find the perimeter of the triangle. So the theorem that we just had told us about points of tangency. What we know is that this segment, CD, has to be equal to CF, right? Do you guys see that? And AD has to be equal to AE because these are the points of tangency, and we've got that relationship when we have some point away from the circle and it sends out two beams, pew, pew, and the places where it meets, it's going to make two segments that are congruent. And these two segments are congruent to each other, and these two segments are congruent to each other. And just for kicks and giggles, this segment here is congruent to this segment here. So how does that help us? Well, if this is 7, FB, Facebook, is 7 as well. This segment is 7. And then if this is 8, then this segment right here is 8 as well. And if this segment is 7, then this whole thing is 10, then this right here has to be 3. So this is 3 right here. So now we've got the whole breakdown of the lengths of the sides. So I know that from here to here is 15. From here to here is 11. This length is 10 feet. And when I add all of that together, I get 36 feet. And that's the perimeter of the triangle. And that's the end of our lesson. So if you have any questions, comments, concerns, feedback, desire for more music, just let me know, and I look forward to talking to you guys soon. Please take care. Bye-bye.